Joint work with Dorel Lucanu, who is a professor at the University of Iași in Romania, and he's also one of the contributors of matching logic. All right, so this is the outline of my talk. I'll try to answer in a few slides what is matching logic, and then I'll go and answer these questions: why and where do we need matching logic? So this is I will highlight the problem that we solved in this paper right there, and then I will tell you a bit about our approach, the results that we get, and I'll conclude at the end. All right, so I'll just go back a little bit and remind you the program verification problem, where you have a program and a specification, and the program verifier tries to answer this question: does the program satisfy the given specification? And if the answer is yes, then you want a proof. If the answer is no, probably you want a counterexample of that. And typically, these tools are based on some logics for program reasoning. And yeah, you can find here an enumeration of the ones that you know. And one of them is matching logic, which was proposed by Grigore Roșu actually in a series of papers. There are many variants of this logic, and they keep appearing. Okay, so that's a different thing. Okay, so here is the general context, and what are the design goals of this logic, of this matching logic, and how is it different from the existing logics? So first of all, the first thing is to use directly a trusted language semantic. So you simply, you can, in practice, you can define your language, and then you can execute the semantics, and you can test your semantics against a test suite. Okay, so this is what happened, for instance, with C and some other languages that we have defined. And besides this, we also have a language-independent proof system, where you simply, the rules of your semantics, they become axioms in there, and then with this proof system, you can start reasoning about programs. Namely, you can derive program reachability properties. So the benefit of having such a language-independent proof system is that you don't have to prove the soundness like you do, for instance, in axiomatic semantics, whenever you add some new axiom in your semantics, you have to update your proofs, your soundness proofs, and so on. So this is proved sound for all languages, if you want to say that. So okay, so this is a generic overview of matching logic, and let me show you how matching logic formulas look like. So you will see here in the syntax of formulas that we have something which resembles the syntax of terms, as we know, and with these terms you can actually build some kind of structure. And these terms with variables, these formulas, we call them patterns, and they're sorted, okay? And the whole point is here that these patterns hold some ingredients that you need in your, that you need to define program for configuration, for example, okay? And besides this, you also have the known logical connectives, quantifiers, and whatever else. And you can also define some derived constructs from these ones, like disjunction, implication, and equality. All right, so I have here an example. And this is a matching logic pattern. This is how it looks like. You have something which looks like a term with variables. You have a symbol applied to arguments. And then again, some other symbol, I just use the infix notation here, applied to some other arguments, and we have variables. And this is what we call a term pattern, all right? And this term pattern, for this term pattern, you can add some constraint, okay? So now, what this means, okay? The intuition is that a matching logic formula is evaluated to the set of values that matches it, all right? So that's the idea. And for instance, this formula here, it matches all the lists that store an array at address, an array A at address P plus 2, and there is some other constraint here which says that at index 3 I have an even number, okay? So if this would be the set of all the elements matched by this formula, then one element here could be this one, okay? Okay, that's just an example. All right, so you will often, when you hear about matching logic, you'll often hear about the K framework. Okay, so the two are linked and they kind of grew up together. All right, and in this K framework there were several languages, real-life languages defined, like the C language, a version of Java, also JavaScript, the Ethereum virtual machine. And there are some other projects that I'm not even aware of right now. So this framework allows you to define languages. And how does this work? You have to specify some kind of program configuration which holds all the things that you need to run your program, like, I don't know, heap, or whatever ingredients you need in there. And these program configurations in matching logic can be represented as patterns, okay? Now, semantics in K is given using some rewrite rules, okay? And in matching logic, these can be, these rules, which look like this, okay, can be encoded as implications, right? So this is the connection between the two. All right, so how does this K work? Okay. Oh, yeah, by the way, so K framework is the best effort implementation of matching logic, so I forgot to tell that. All right, so how does this work? The idea is that if you have an input program configuration, an input pattern, say T and phi, and you try to apply some a rule to this T and phi, so all you have to do is to compute the set of common elements that matches both patterns, all right? And only those elements transition to elements matched by the right-hand side of the rule. And this is called semantic unification matching logic because intersection, this conjunction here, gives us precisely the intersection between the two, all right? And well, these kind of formulas are actually the root of problems for that, the root of the problem that we're trying to solve in here. Namely, the fact that we have this kind of structure, these term patterns occurring here and here, and this is problematic because if I give you a formula like this, it will be kind of difficult to understand what it means, okay, right from the beginning. So having multiple term patterns in a conjunction like this might be problematic from the user's perspective, because if some tool provides you with something like this, well, it might be difficult to understand what's going on there. But also in your tool, it adds some complexity, because for instance, if you want to check whether an element matches the given term patterns, all you have to do is just to iterate through all of them, and that's quite inefficient, all right? So this requires also some more time to process, probably need more space. And there is another technical aspect. You cannot use SMT solvers to simplify these things. So what are we trying to resolve here is that can we simplify patterns such that they contain only one term pattern all the time? Okay, so that's the question that we want to answer. And if I go back to my example, I notice that first, this T1 here and this T2 here, they must kind of have a similar structure, because if they don't, then I would not have any inhabitants in the set matched by this conjunction. So the thing is that can't I just keep one of them and then add some equalities that make the two, that keeps the connection between the two, right? So and in this paper we show, we show how to do that, how to compute this formula, this equality, using syntactic unification. All right, so that's one thing. Why would you want to do that? Well, first of all, you want to have only one structural component, and the second thing is that formulas like this are very, so you can send those to SMT solvers, and in the implementation, this could be very helpful. You can simplify the formula for you and so on. So this is really helpful in practice. All right, so the contributions are listed here. So we use syntactic unification. So we show how to use syntactic unification to compute this formula. We prove that our approach is sound and complete. And yet another thing that we're trying to do in order to improve the currently developing matching logic implementation is that we try to generate certificates for these reductions. All right, so we try to generate proofs because we want, since this is automatic, we want this to be included in the, I don't know, bigger certificate that we want to generate with the matching logic implementation, with the matching logic proven implementation. So this is also an important contribution that we make. All right, so I'll go back and tell you a few things about syntactic unification. Probably some of you are familiar with it. So we know what terms are. We denote substitutions like this. So I have variables and terms. A substitution is more general than another one if, well, this one is just a particular case of this one. And a substitution is said to be a unifier of T1 and T and T prime. If applied to them, it produces the same thing, right? So that's a unifier. And we say that substitution is the most general unifier of two terms if it's a unifier and if it's the most general substitution with this property. All right, so now in order to introduce you the syntactic unification algorithm, I'll have to define what is the input of a syntactic unification problem, and this is how we define unification problems. You have pairs like this or bottom, okay? So it's just quite simple. And we say that sigma is a substitution of a unification problem if it is unifier for every pair in this list, okay? And we also say that a unification problem is in solved form. That's the goal that we want to reach. If these pairs have this form, where you have variables on the left-hand sides of this equality, and these variables never occur anywhere else in the unification problem. All right, so now this is the classic syntactic unification algorithm. The idea of this algorithm is to, if you want to check whether T1 and T2 are syntactically unifiable, you simply build this input, okay? And then you apply a set of rules, and in the end, you'll get a solved form for this unification problem, which can be either success, where you get the MGU, and this is proved that you get the MGU if you finish applying these rules, and otherwise you can get a bottom, all right, which is failure. So how can this fail? Well, it can fail if one of these two rules apply, the rules below the line. So the first one says that if you try to unify f of something with g of something, then this fails, of course, because they are syntactically different. And the other one essentially avoids the cases when you try to unify x with f of x, for instance, and that's a bad case as well. So if these two apply, then you're in trouble. If only these above the line apply, then you'll get the MGU. These are some properties that were proved in a paper a long time ago by Martelli and Montanari. Okay. Now, what do we do with this? Okay. So given T1 and T2, that's our input. We simply build our input like this. We run the algorithm, and we get some substitutions which look like this. And we simply compute that formula that we're looking for by simply putting an equal sign here and make a conjunction of all the substitutions that occur here. Okay. So now, in order for this to work, we need this is more technical. So we need to work under some set of axioms that ensure the fact that our patterns that we work with they resemble terms, because in matching logic you can have two different symbols with the same interpretation, but in practice that doesn't happen. So we need to work under that set of axioms. All right, so the first result that we have is this one, which is kind of expected. If the syntactic unification algorithm gives you some results, some MGU, then you'll have the equivalence between the formula that we compute and T1 and T2. And this is something you might expect. And the second result that we have is that if syntactic unification fails, then you can, under a slightly different set of assumptions, of axioms, sorry, you can show that T1 is different from T2 in matching logic as well. And this set of assumptions essentially contains two axioms that simply avoid the cases when you have symbol clash and occurs check in the model. Okay, so that's just, again, technical. And in practice, this is true. All right, so what do we mean by unifiable term patterns in matching logic? And we say that T1 and T2 are unifiable in matching logic if this formula is satisfied, and essentially it says that there are some values for the variables of T1 and T2 such that the set of that matches this pattern is inhabited by some elements. Okay, so that's the whole point. All right, and okay. All right, so here is the soundness, and for the soundness, what do we prove? Essentially, we're trying to run the syntactic unification algorithm and see what happens. So if the syntactic unification algorithm gives me some MGU, then T1 and T2 are unifiable in matching logic, and I also have this equivalence, which is really important. So this is the main result, in fact. If you get bottom, so T1 and T2 are not syntactically unifiable, then it means that those are not unifiable in matching logic as well. All right, so for completeness, we're trying to do it the other way around. So if T1 and T2 are two-term patterns, if they are unifiable in matching logic, then they are unifiable in syntactically, okay? And if they're not syntactically unifiable, then, if they're not unifiable in matching logic, they're not syntactically unifiable. So this is, the converse property. All right, so now very important is this part of generating proofs. So one of the things that there is this company of Grigore Roșu, they work on developing on a matching logic prover, and they try to use lots of simplifications and things that might help their implementation. And the question that they had for us once we showed them this was that, okay, can you also produce a proof that uses the rules that we have in the matching logic proof system? And they want this because since this is automatic, and it would be nice to also have a proof of it, because if you apply it, you want to have everything in a proof certificate, which can later be checked by a proof checker. And we said, okay, let's try it. And it looks like the thing is not that difficult. So the whole thing to do was to simply add a new set of rules to matching logic. These are some derived rules. Each of these rules can be proved separately using the matching logic proof system. And the nice thing is that every rule corresponds to a rule in the initial syntactic unification algorithm. So every time when you run your syntactic unification algorithm, you can actually see which rules have been applied, and then you apply in your proof, you apply precisely the rule with the same name. So you simply keep that execution in mind, and you have a proof, okay, for that. So this one-to-one correspondence seems to be the key of generating proofs for this case. All right, so here is just an example. I don't want to go through all of it. It's just that I just want to tell you that, well, we use a proposition, which we have to use this proposition always. And this is also proved using the matching logic proof system. And then all the other steps in your proof are based on the rules on these derived rules, okay? And this is more or less like a proof certificate, and they're trying to implement right now. All right, so we've seen that unification algorithms are useful in matching logic for simplifying complex patterns and for generating proof objects. Recently, new versions of matching logic have been published, and one of them is this applicative matching logic. And the nice thing about this is that they have a proof checker whose implementation is in mod. And one thing to do would be to update this work to that to actually check our proofs automatically. That would be one thing. And the other more interesting thing to do would be a further investigation in unification modulo axioms and see how can these be encoded, represented in matching logic. So I already started with Professor Lucanu to work on this unification modulo associativity, and this applicative matching logic has a fixed point operator mu, and we're trying to use that to represent infinite sets of unifiers. But yeah, we have some preliminary results, but we still have to work more on that. So thank you for